The 2025 Nobel Prize in Physics has been awarded, and the work it celebrates confirms something profound, that the universe, at its heart, doesn't play by the rules we know. For most of the 20th century, the weirdness of quantum mechanics was locked away, a secret world for electrons and atoms, too small for us to see. The world we live in, the world of baseballs and cars and walls, that was a classical world. The 2025 Nobel Prize in Physics was awarded to John Clark, Michel Devoret, and John M. Martinis for their experimental work for quantum tunneling. Imagine you're in a room with no doors. If you throw a tennis ball at the wall, it bounces back every single time. That's the classical world. Now, shrink that scenario down. Shrink yourself to the size of an electron and make that wall incredibly, impossibly thin. In this quantum realm, when that ball hits the wall, something impossible happens. With every bounce, there's a small but real chance it doesn't bounce back. It simply appears on the other side, as if it phased through solid matter. It's the best explanation. A particle doesn't have one single address. It has a wave function, a mathematical cloud that describes where it's likely to be. The peak of the wave is its favorite spot, but the wave has tails that fade out, never quite reaching zero, meaning there's always a vanishingly small chance the particle is somewhere ridiculous. So when this probability wave meets a barrier, most of it reflects, but a tiny part of that wave leaks. It seeps through the wall, carrying with it the faint possibility that the particle will manifest on the other side. This isn't just a theory. It's a real engineering problem. In the computer chips that power your life, components are now so small that electrons can quantum tunnel across gaps they shouldn't, causing leaks and errors. But for decades, we thought this strangeness was exclusive to the ultra-small. Then, in the 1980s, a team at UC Berkeley asked a revolutionary question. Could this quantum weirdness happen on a human scale? They turned to a specific setup, a Josephson junction. Imagine two superconducting wires with a thin insulating wall between them, an impenetrable barrier. For a single classical electron, this wall is a dead end. But in a superconductor, cooled to near absolute zero, electrons don't travel alone. They form Cooper pairs, and billions of these pairs move in lockstep, described by one giant collective wave function. When this macroscopic wave function reaches the thin barrier, it doesn't just stop. Its probability field extends into the wall, overlapping with the field on the other side. This overlap allows the entire collective, billions of electrons, to tunnel through as one. This effect won Brian Josephson a Nobel in 1973. But the Berkeley team wanted to go further. They wanted to see if the entire wave function itself, this single quantum object representing the whole superconductor, could tunnel as one. To test this, they had to create one of the most isolated environments on Earth, cooling their junction to temperatures colder than deep space, shielding it from all outside interference. They passed a current through the junction. At low currents, it behaved as predicted, a supercurrent with zero voltage, as Cooper pairs tunneled through. But then, they cranked the current up, and at a critical point, something counterintuitive happened. A voltage spike. This was the signature. It meant the collective quantum state, the entire wave function, had escaped. It had tunneled across the barrier, not as individual particles, but as a single massive quantum object. Now, you might be thinking, how do we know it was quantum tunneling? Couldn't it just be heat jolting it over? A brilliant question. And the answer is in the cold. At higher temperatures, random thermal energy can kick the system over the barrier, a classical process called thermal activation. But as the Berkeley team plunged their experiment to near absolute zero, eliminating all thermal energy, the tunneling didn't stop. The escape rate became completely independent of temperature. It was no longer a classical process. It was purely, undeniably quantum. The universe was showing its hand, proving that quantum properties aren't just for tiny particles. They are a fundamental feature of reality, even on scales we can engineer. Back in 1935, Schrödinger used his infamous cat to argue how absurd quantum theory sounded when applied to the large scale. But here we are. We didn't get a zombie cat. We got something better, the foundation for the superconducting qubits that power modern quantum computers. This curiosity-driven experiment, this decades-long pursuit to simply know, unlocked a technology we are only now beginning to harness. That is why this work feels so worthy of a Nobel Prize. It didn't just confirm a theory, it expanded our reality. You've made this far without your wave function collapsing, and we'd like to support the channel and the content that we make. Hit the like button and subscribe if you like the video. Until next time, take care.